welcome to Swiss-Sino Science Club. Our topic today is the Markov decision process with observation cost in food safety. Our two speakers are Professor Josef Teichmann and Tengyingzi Perrin from ETH Zürich.
Finally, some peace and you can concentrate on research.
Great.
Good. Welcome, everybody. I hope to introduce you to the first joint seminar of the SSSC, Sino-Swiss Science Club, with popular science talks. You will see my talks on the popular. It will stay funny. And but Sophia, my PhD student, she can of course make very understandable what she's doing, and you will see it's an important subject she's working on. And I'm particularly happy that we have this joint seminar with my working group seminar, which is on Friday evening, when my duties as head of department somehow fall down. What I like to do in research. And well, I think we can start. Take your time, Sophia. I still need to finish my slides.
Yeah.
And please ask questions. It's a very open seminar. So you're supposed to talk and to ask whenever you feel there is an open question. And well, do you want to say something?
Sure, but you have said something on behalf of me. So, of course, good evening, everyone. So it's my honor and it's my pleasure to be invited as the host for this special seminar. Okay, Swiss-Sino Swiss-Sino Science Club Popular Science Talk Session 132. Okay. I cannot remember for a long time. So let me introduce myself. So my name is Zhang. I was here as a postdoc of Professor Alessio Figari in the Department of Mathematics in ETH. So, and I have given like twice, I think, in this science club. Like twice talks, but one is kind of successful, and the other one is too theoretical. So and it's like a failure.
You will see people will remember your talk and think, in comparison to my talk, it was a success.
Well,
will come back on that.
Thanks.
It will be rehabilitated.
Thanks. So okay. So now I'm coming back to visit Alessio, and it is my pleasure to see new friends and old friends, of course, and also to join this session. So today, our topic is about the Markov decision process with observation cost in food safety, and we have two distinguished speakers from the Department of Mathematics at ETH Zürich. So one of them is Professor Josef Teichmann, who spoke already many important things for this seminar that you should ask questions, and it's a very open seminar. And the other one is, I think, his PhD student, Tengyingzi. Martins, or what? Okay, I hope I did not memorize your name wrong. Okay, so
I'm not the only one who has this registered for now.
So practical. So I'm not so practical indeed, even though I'm studying kind of applied mathematics. But you know, even though we call applied mathematics, it's like about PDEs and calculus of variations. You just say these things are useful, or say these things have a background in finance or in physics when you apply for the foundation. Otherwise, you just, well, we don't care. It's just something we want to we have interest to study something, or say there is some big open problem and we are concentrating on it. So, I mean, it's very interesting for me to see real applications, say like this Markov process in the food safety and things like this. So yeah, it's my pleasure, I think, and to learn something new from maybe real applied mathematics. So I think now it's time to let our first speaker to talk about her session.
Yeah,
So
thank
please.
you. Yeah. I want to first thank you for the organization, and it was actually more work than we expected. And thanks for inviting me also, and thanks for Josef for joining. And like what he just introduced, as a mathematician, we don't really care about the applications. We have something that we're interested, and if it can be applied in some parts, and we're happy about. So today's the topic is it can be applied in food safety, but not only. So it can, of course, applied in other fields. And it's a joint work with Florian and Josef. It doesn't work. Okay. So my project is actually a big collaboration with a lot of researchers from food safety or microbiology. And basically, we have this idea of proceeding our project, and we discuss with them like what kind of problems they have, and then we try to solve it. And today I will keep also less mathematics in my slides, and more like I hope that for people with different background can take back some knowledge that they didn't know before. But for some people who's experienced in reinforcement learning, maybe it can be boring. And first, I want to introduce the background. So all the subject we are working on is because of this bacteria called Bacillus cereus. And this bacteria you can find everywhere in soil, water. So of course it's in food, all kinds of food. And normally the bacteria has vegetative cells and the heat-resistant spores. So for the vegetative cells, it can produce heat-resistant toxins, and this is the major reason that can cause foodborne illness like vomit and diarrhea. And they have varieties of strains of Bacillus cereus, so they have different types of them. And some of them, they can actually be used as the pesticides. And it's widely used actually because it's somehow natural, more natural than the chemical ones. But that's why that we have this serious problem that we even use it as a pesticide, but we still don't know much about how it generates the toxins. And because at the moment, they observed that different groups of Bacillus cereus are together, or when they mix with other bacteria, or at different temperatures, they produce different kind of toxins. And some toxins are like low level. It's not very dangerous, but some can be very dangerous. And for the spores, it's heat resistance. So normal heat cannot kill it. And after you eat the spores, then it start like in your digestion system, it became vegetative cells, then produce the toxin, and that's the problem. And the whole project is about to build a safe chain of like a food system. And so we can manage the microbial risk. And we also want to minimize the food waste while protecting human health, biodiversity, and ecosystem. And now I want to introduce the method. So here is the Markov decision process. It's actually the mathematical foundation for reinforcement learning. So basically, we have the agent and we have an environment, and the agent needs to do some action, and then the environment can give some feedback. So we call it a reward. And from the reward, the agent learns how to interact better with the environment to get better reward. And for the state is some values that the environment can show you the state of the environment. And here is some notations. So for a Markov decision process, we have a set of states, actions, also action space, and the time, and the transitional probabilities, and the reward function. And the discount factor is to have, so we prefer to have an earlier reward than a later one. But in the Markov decision process, we have a problem in reality, which is that it assumes that you know all the states. So you know how the environment exactly, what's the states of the environment. But in reality, this is normally not the case. So they introduced the partially observable Markov decision process, meaning that we cannot access all the states we want, and we can only access part of it, which we call it observations. And so underlying, it's still a Markov decision process, but we cannot observe all the states. So we can only estimate the real state based on the observation we get. And in most of the cases, the observation we get has limited information, so you cannot get a good estimation. So we think normally you take the trajectory of the history. So the observation history would tell you more info about the previous observation. And so here the policy is memory-based because you need the history of the observations. And we introduce the Markov decision process with the observation cost. So it's something in between of the Markov decision process and the POMDP, so partially observable one. Because in our case, we give the observations. So for each observations you want to observe, you need to pay a price, which is very realistic because for example, in medical test, that if you want to see how safe or what action you want to do next, then you need to do a test. And this test often very expensive or it takes time. So meanwhile, when you do the test, maybe it's become already more dangerous. So this is not what you want. So maybe you should limit the time of testing, for example. But on the other hand, if you don't do any test, you don't have much info about it. So in our case, we added the mask. So M is the mask that can, at each time step, that the agent can choose which state it wants to observe. And by observing it, it needs to pay a price. Here is the C. Here it shows the cost. And we give right now the state. So the state, I think it's better to call it observation here. If you choose to observe at for example, at T, then you get the real state. But if you choose not to observe, you can only get the history. So the formal ones, formal history. And in the end, of course, you still want to maximize the reward. 啊，这个不太重要。对，因为那都不要紧。它不是很容易关。Okay. Okay. So here we define a set of policies. Policies is for example, it's a neural network that make decisions, and it's a sequence pi t, and it's a function taking the history of the states and the actions, and to decide probability distribution for your next action. And we also define the value function that is the expected reward, expected future reward. So if I take this action, how good can I get later? And I want to now introduce some reinforcement learning to solve this problem. And right now here is not all, but mainstream reinforcement learning algorithms. And I will introduce later the more in detail so you can understand what's the differences between them. And first, they are grouped. Yeah.
Other than the curious about the previous one.
Mm-hmm.
I think there's a circle dot.
Which one?
Also, maybe slide. Yeah. So on the observation process.
Yeah.
So there's a circle dot which is applying the mask, right?
Yeah.
And why you couldn't choose the same thing for SD and SD plus one?
Because because here you choose, so when empty here, if it's 1, so you choose to observe, then you get ST plus 1. If you choose not to observe, then you only get so you see, if empty is 1, then you choose to observe, then you get ST plus 1, right? If you choose not to observe, then you don't get ST plus 1, but you get the history, so ST tilted. So that's the idea. Yeah.
Thanks.
Okay, so we're coming back to the reinforcement learning approaches. And now I will introduce the different kinds of algorithms. And the first, I want to say that they divided into mainly 3 groups: value-based, policy-based, and actor-critic-based. And first is the value-based algorithm. So I hope you still remember that the value function I just introduced. So in the value-based algorithm, what we want is to maximize the value function directly. And the most important or the most famous algorithm for value-based algorithm is the Q-learning. And so the Q-learning is the value function. And at each step, you just compute all the Q values, and then you choose the one with the highest Q value. And that's very direct algorithm. And so you can see that what it wants to get is the total future reward, like to maximize it. And yeah, so here is an example, and normally it works better on when your choice are discrete. So the action space is discrete and not very high dimension. So it's more direct to know like which action to take. And for the policy-based algorithms, instead of looking at the value function, we take a look at directly the policy function. And so it's like you directly update the policy and to get the better to go to the you update the policy and have an action that can give you the better reward. And so you just normally in my case, the policy-based algorithms are performing much better. I guess it's because my action space is rather large, and but I tried to use the Q-learning, but the training is very unstable. Yeah.
So excuse me, what is the difference between this policy function and the value function?
So policy function is like a it's like you have a agent, expert, an expert to tell you what to do later. And it's a function. Yeah, exactly. So this policy is basically your network that it takes input. So the input is state and the action, or sometimes only state. And then it tells you, okay, next action, you should do this. But the value function is just how much you can get later, like how much reward you can get afterwards.
Less variables?
Yeah, it's mainly you just calculated number, but for the policy function, it's the output is the probability distribution.
So can I have
When you think of stochastic control, so the policy is the control, the value function. Usually in machine learning, the control is relaxed. As you say, stochastic control, meaning that we do not go directly to control in the control space, but to distribution.
I see.
Just to relax the problem, make it more linear, but easier conversions.
I see.
Yeah. And then the next one, yeah.
Would you, like, for these different algorithms, would you build a parallel to stochastic? Like, is there counter, like, okay, that's like, me control is somehow a special thing. Can you, I mean, there are like typically two techniques, right? There is more something inspired by the value function, would be a dynamic programming principle approach. While instead this policy algorithm would be something connected to the maximum principle, I guess.
I mean, you can look, let's say, from a fundamental perspective, when you do discrete stochastic control, not time continuous stochastic control, they are precise counterpart. And you know, in control, there is one lagging perspective, there's the dynamic programming perspective, and you can always relate it one-to-one to these algorithms. What is a little bit unusual in stochastic control is the feedback. Usually we do not think like that this is more in this discrete setting, but this is also nothing very special. Just an intermediate step in the dynamic programming principle they're giving me. So in that sense, yes. But if you consider continuous time, you run into some difficulties. For instance, relaxation continuous time is massive, since you have at each point of time measure on control space, and when you sample from this measure independently, you have an uncounted number of independent services and less. There one needs to think. So what is in discrete time an important tool, and the simplification of the problem appears to be in continuous time more evolved. So in that sense, not always counterparts in continuous are not easy to construct.
Okay, I shall continue. Yeah.
So I just wonder, I have a question regarding the distribution of actors per tape.
Mm-hmm.
So why is it like it's a distribution rather than like a, say, a probability of one of taking one certain action?
I think for example in
Because I remember like I think I took a course like some time ago, and it was like I remember there's a assumption or like if the action space or the something like simplex, and it's always the optimal action is always to put all your weight or the probability weight on one action, right?
Yeah, can you try?
I'm sorry.
下期
Yeah, but I mean, I remember the assumption that is like I remember it seemed to be like the action space is like a simplex, and then the optimal action or optimal strategy is always to put all your weight, probability weight on one action.
This is true, but when you consider algorithms, so you control this thinking instead of actions, measures on actions is first a tool which is called relaxation. Just allows to get easier system. But what you say is completely correct. Often the solution of the relaxed problem is concentrated in one action. So it has a probability one solution. It's the same solution. From an algorithmic perspective, this is an advantage to be relaxed. Because it's related to what one calls exploring. That even though you are quite sure that this is a good strategy, you still try and
Oh, the exploration.
Yeah,
dilemma.
exploitation would rather be that you're very sure this is a good strategy. Exploration is often what you need to do because you did not solve the whole problem. You're just away and therefore exploring.
yeah.
Relaxed problem and the rhythmic heavy.
Yeah, and also I think during training you can actually choose. So if your algorithm is deterministic, and then and also for one algorithm, but it's not in policy based. It produce the value instead of probability distribution. So not all of them give you the probability distribution. Yeah. And so, of course, with the two families of the algorithms, someone have the better option, of course. It's called actor-critic based. So you basically have two networks that combine both of them. And so the one is the actor that can tells you what to do, and then the critic then tells you it's good or bad. So give you immediately feedback. It's kind of like GANs. And the algorithm is A2C, SSSC, TD3, and PPO. And the PPO, sometimes it's also, some people like to put it in category policy-based. And I think it's okay, but I prefer to put it in actor-critic because it also uses both. And this is exactly an example. So the actor do some action, and then the critic tells the feedback, and so the actor can improve based on the feedback. And for the on policy and the off policy, the on policy is that for each time at each time point, agent runs a few simulations. So it learns a little bit, and then it updates according to this experiences, and it forgets when it moves to the next time step. So each time it needs to generate the new experience to learn. And this, they call it low data efficiency because for the past experience, it already lost. And for the off policy, it just can always generate, and it can save and then it randomly takes some of the past experience and to learn from the experience. So this experience is not only, it can be like from all the other policies to update the current ones. It can also, of course, include the current experience. So it can be high data efficiency. And now I will introduce our applications. So first, in the food system, we focus on the manufacturing. And we apply our model in the milk powder production chain. And as you can see that we use this simulation that the milk would go through the heat exchanger for preheat, and then the holding tube to control the microbial load reduction. So here in this case, the microbial load we are talking about is the vegetative cells. So I hope you still remember that I said the vegetative cells can be removed with the high temperature. And the evaporator for pre-concentrate and the spray dryer to dry the milk into powder. And here the states is the mass, so how much milk get into the flow, and compositions, so how many % of proteins and etc. in the flow, and the temperature, pressure, quality. Here we use the because I think there's no like no info we can find about the quality, so we use the very simple one that's based on the protein and the carbs. We decide the quality and the microbial loads. And for the observations, we basically just add some noise on the state. And we give also them different price to pay, because I think the quality and the microbial loads would take more time, so it's more difficult to get, so they have higher price. And the compositions, the next is has in middle price, and then the mass, temperature, pressure are relatively easy to measure, so they have lowest price. And the actions we can take here is, as you can see, it's not very critical for us, but those are, they have 6 parameters we can do the action, and the plus the M is the mask to decide which state we want to observe. And for the reward, we classify the product based on the microbial load and the quality, and we set a price category for each category, and then analyze the profit loss, and this of course include the observation cost. And this is we actually run 3 different scenarios. So first is that we run MDP. Scenario is that we observe everything. So we observe all the states. And the POMDP is we don't observe anything. So what we have is only the state at time 0. And then later we don't observe anything. And the MDPOH is our method that can choose what to observe. And you can see here, when the cost is 0, means that even if you observe everything, you don't need to pay. Then the performance is similar. So it also shows that in this environment that is quite easy to predict for the model. So it doesn't need to constantly observe new things. With the initial state, it can already predict well what will happen later, so it can do good decisions. And here is the training curve. And you can see that MDP is the black one. It converges a little bit better than the others. And the MDPOC 1 is in the middle, and the worst is POMDP, but in the end, they are all very similar. And when the cost is 30, at this time, you need to pay for the observation. And you can see that the MDPOC and the POMDP are having similar results. And MDP is the lowest because it needs to pay every observation. And from the learning curve here, you can see that the MDP, I guess, at the beginning, it chooses to pay. And then it realizes it's useless to observe. So it just goes to more close to the POMDP case. And the result is still similar. And if now it's reversed, for example, if knowing more information is actually much better to make you make better decisions, then I think our algorithm can also choose to pay, and in the end find a balance between the cost and how important the information is. And for our second application, we extended the system. So now it's from farm to manufacture and then to sell to the customer. And it's actually very simple. So you have different farms with a different quality of milk. And as a factory, you need to buy the raw milk and then sell it to customers with different standard. And so what you need to do is you need to choose milk to buy and then choose a customer to sell. And here is our action space. Is the first you need to select the farm, and then you test. So after the milk powder is produced, you decide how many tests you want to do, and then you choose the customer, and you sell your product to the customer. Then customer also will perform some tests. If the result they get from the test is below their threshold, then they reject or you get a punishment. And in our case, we also add the cleaning action, so the agent can choose when to clean the pipeline. And the observations here, we only have the observed spores and the time step. So we need to know at what time, like how many steps we are, and also the phase info. So I want to say that in our applications, we have a quite unusual setting, because normally, for example, in chess or in, for example, if you have a maze and robot needs to find a way to be out, but at each step, it kind of what you can do is the same, like you go upward or you go backward, and it's almost the same at each step. But in our production chain and also this process chain, at each step, your action is different. For example, in the in the first time step, you first select a farm, and then you change to the next step. It doesn't matter what you change for the farm, but now you need to decide the test number. And also for the previous case, in each component in the process, the environment is completely different, and so the actions are completely different. So here it's important your model knows that which phase you're in, like in which component you are in. So we think this info is definitely, we need to put it into the training. And for the farms, we have a few assumptions, is that each spores level from the different farms follow a given probability distribution. And we actually got from a professor, and I checked that the distribution, the variation is very, very high for the spores. And so we categorize the farm into low, medium, high quality of the milk, but even within the category, the variation is very high. And also we assume unlimited supply So it means we can always, if you choose to buy low quality milk, there's always ones you can buy. And the spore testing is not performed at the time of raw milk collection. So when you go buy the milk, the only data or info you know about the milk is only the number they provide you. You cannot do any test because the time reason you really don't have time to do the test. And for the milk powder factory, the maximum operation time is 24 hours, so 1 day. And this lag phase is how the spores will develop during the process. And you can see that it roughly follows this function here. And the cleaning process duration is 6 hours. And normally in the factory, what they do is they run the process for 18 hours, and then the last 6 hours, they do the cleaning of the process. And then the next day, the same. Yeah.
The moving of the two systems, like in the previous one, you add some noise, right? How do you add the noise? And then why, like, you pick noises on, you add noises, like, so those two are all simulations, right? They're not real world like data.
No, yeah, it's all this one we use some data, but mostly simulations.
Well, like in the previous one, you add some noises.
Yeah.
Right? But on this one, you haven't add some noise. So why do you pick this?
We have noise.
So also on this, the second system, you also add some noise.
Yeah, we also add noise, and also because we observed, like what I said before, that the first environment, we think it's very deterministic, so it's very easy to predict. So this one, we made it more dynamic. So like even though you observe now, you don't know what will happen later.
Like choose your noise like strategies, like Gaussian noise, or like
Yeah, actually for this one, we asked the professor how they normally deal with the data. I think for so here, this one, we added for the spores level, we added the Gaussian noise. And later for the testing, it's what's the name? I forgot the name. But we used another, yeah. And for the customers, they can decide how many times they do. And then if the spore levels exceeds the standard, then a penalty will incurred. And this is the first result we got, over 1,000 episodes. And you can see that our performance is also still much better than the classic. And the PPO we used has similar performance as the RNN PPO. It's just you add the LSTM before the PPO. And here is the training curve. And then I try to make it more dynamic and the problem more realistic and of course more complicated. I extended, of course, the operation time to like 2 days or 5 days, more realistic. And then I added contamination accumulation. It means that when the milk goes through the pipeline stays. So after the milk is produced, produced into the milk powder, there's still spores living in the pipeline. It doesn't for example, before in the model, each time the spore level you get is just the initial ones. And right now that if you don't clean, then it accumulates more and more and you have to clean. And the cleaning effectiveness, meaning that maybe each clean, it doesn't remove 100% of the bacteria. And so it has a randomness here. And the rare high contamination sample, it's actually, we visited a factory before, and they mentioned they have a problem because it's a powder. So when they do the test, they often have the case that some powder maybe was like with some moist, and then it's very easy to have the bacteria. But this is very difficult to detect because it's very rare. Like you have a batch of the milk powder, but maybe just at the corner there is some contamination. And if you don't do enough tests, then you cannot find it. And now you can see that I tested different algorithms, and from this training curve, you can see that they perform almost similarly. But if you see this is the evaluation curve during the training, you can see that the one with recurrent, so with the recurrent layer, is much better, and it suffered less from the overfitting. Yeah.
What's the motivation for introducing R network?
Yeah, because at the beginning, when I introduced the POMDP, that we think with the history. So how to deal with the history? We normally use the RNN to deal with it, and we think it's better. But because I think before our environment was really easy, so it always performed similarly. But when we increase the complexity, now you can see that how much better it can be. Just the LSTM, yeah, yeah. The structure of all the models are very, very simple, like a small, very small network. Yeah. And here is the result that you can ignore the PPO one because here the result is actually the best performed of all the training. So I saved the best models, so the PPO should be has similar performance, but here I think I saved a different model or something. But anyway, you can see that they perform much better, and also from the previous one, we think adding the LSTM layer is a better option. And I also want to say that we are also like now, I think I would work on adding the LSTM on also the TD3 and also the SAC. And also we are considering to deal with the time series. So to deal with the history, that it would be good to use the attention layer to replace the LSTM. And that's what we are going to do later. And thank you for attending. Yeah.
Thank you very much for your very nice talk. I think you asked the wrong host. This is too realistic for me. But is there any questions from the audience?
Yeah.
Somebody. Like, can we go back to page number 47?
Yeah.
For this curve, like, can you explain more with this curve? And then
Yeah, just during the training at each 10K step, I perform an evaluation. And then you can see that I didn't do this before because the models are rather, each time when I do the evaluation, it's very similar as the training result. But then when I did the evaluation, I can see how bad they performed, and it was shocking. And also when during the training, it's actually very so the performance is not always like this. So like the order is it depends on the like which time you perform.
how do you say like the flat, like
Flat one is just I didn't it actually it's not flat. It just maybe go a little bit. It changed a little bit. It's not the same number. Also because
the PDO is like higher and then with more fluctuations?
No, I don't think it just so first when it's flat, it's actually not flat. It changes a little bit.
Yeah, like changing the gain, like it's changing small, like
Yeah, yes, yeah, it's not so much. And also because I didn't smooth and like I take every 10K evaluation, so it changes like this. It's not like a curve. Yeah.
And also like, how like first one is why we use like our reinforcement learning for like the task comparing with like the traditional one, where like even for the first task we can use like PID control or something else for like finding the optimal solution. And what would you think is the advantage of the reinforcement learning?
Yeah, I think so like I said before that I think we didn't have the problem first and then we find solution. It's like we have something we want to do first and then we find some problems that we want to solve. So in our situation, I think reinforcement learning can target better on all kinds of questions, like a similar issues. And then it doesn't, for example, for the first one, I told you it's because the environment is very, very simple. And so of course you can find I think maybe a simpler solution to make it work. But when you add the stochasticity, then the problem become different. Yeah.
Yeah, I'm actually curious about how you choose this topic, this specific use case in food safety. Because when we talk about reinforcement learning, the use case coming into my mind is more like robotics, or you know, like Chinese, or training large language models. This is like a very special use case that I never saw. How do you find this topic, or is it because of only you or your own interest, or because of foundings?
I think both. I think both, because I'm also I often very interested in like medical or like health related topic, and that was one reason. And another one is I think Josef would think this topic is also quite interesting too.
I would ask you, then, abstractly speaking, what is the difference between a robot which knows to move in a certain environment and a controller who knows to move optimally in this environment? Conceptually,
Mathematically,
yeah.
I think one of the challenges in R was the over optimization problem. So there any possibility that you bring the algorithm that it is the reward hacker. So how do you provide this kind of thing?
So at the moment you can see the performance that it just most of the algorithm has the overfitting problem. And but when you check with the so I always take I feel you can see that it just converges or have a good solution very fast, because when I do the evaluation, the result is quite good if you take the best performed model.
I mean, the baseline is approximately 2000, and the highest reward function is like 10,000.
Yeah.
Is there a possibility of over optimization?
This I don't think so, because I feel that in the real cases that maybe the baseline policy here, I always choose the best milk and to test it 3 times, and then based on the test you select the customer. And I think normally maybe with the expert in the company, maybe they have better knowledge. So maybe the performance is better than this. And but the idea of our the advantage of our algorithm is that we can always adapt based on the reality, because in the company that we talked with them, they always have a very rigid process to go through, and they don't change much. And in our case, that's based on for example, if the milk quality is not so good, then you can change the strategy. And if you detect that it's more dangerous, then you can choose to clean. And this is like to adapt based on the observations. But in reality, I think they don't really do that.
In those cases, your SSC overfitting problems because then it does not perform in new scenarios. Because you can test the performance in unseen scenarios of the algorithm. It's like with a robot, but you know that you overfit your strategy if you put the robot into a new situation and the robot doesn't. You know, something wrong.
Okay, last question. The reinforcement in robotics, why it's possible is because now we have the good simulation, can have the good reality. So in this food chain or food supply management, how do you ensure your model you created is corresponded to the reality?
So for the first one, the first one, I think it follows a very detailed implemented model, followed the physics rules. And I think that one is quite reliable. And for the second one, I cannot say it's very realistic. We just try to make it more realistic. And we have some help from really the experts from the field. And then later, maybe we would also like he could get more data from the real companies and to improve it. So yeah, you can, I think you can not for this kind of things because it's difficult to gather the data. And so you can only try to make it more realistic.
Welcome to the second part of our session tonight. So our next speaker is Professor Josef Teichmann, and his title is the generalized. Okay, I don't know how to pronounce it correctly.
It's not so Langevin.
Langevin.
You can say it quickly.
Langevin dynamics and generative AI.
Yes.
A very popular topic.
Very popular topic. Very popular.
Okay, so please.
I mean, popular. It's interesting. It's one of the technologies of our times, which are very interesting to study. So this is a joint work with my friend Feng-Hui Yu. She's currently team guest, not so long anymore, so we finish soon the work. And we think about technology you all know. I think everybody in the audience has heard about DALL-E, this OpenAI technology, which is a combination. Who knows what it means, DALL-E?
You mean the image generation?
No, but why the name DALL-E?
It's art.
There's the artist DALL-E, but there's also Wall-E for the movie. This brings those together. DALL-E and Wall-E. So DALL-E. Therefore you have the E at now. So DALL-E and Wall-E is creating, generating new images. So we're not talking about storing a lot of images and then you give a prompt and then one of the many images is taken and given you as an answer, but storing a lot of images in a neural network in a certain architecture, then you give a prompt and you get something which is not copy and paste, which is new. So sampling from known images, pictures, paintings, new ones, unseen ones, given a certain prompt. That's something which we have never seen before, which we did not see before, and it is obviously a technological breakthrough. What I find personally even more exciting or funny about this is the mathematical concept which is behind, because it is actually a quite deep theory which is there behind, and they try to motivate a little bit what it is, and then what we try to generalize there, and why there's a point in generalizing this. So just in comparison, when you look at large language models, the model behind the large language model is not so complicated. There's also some theory, of course, but it is not something where you have to study stochastic analysis for a while in order to understand that this type of model can work. What is more surprising is that it does work, because it's a very simple model. Here it is also more surprising that it works, but the model behind is not so easy. So not so easy to understand. And I will try to explain a little bit why there's a point in generalizing it. As I said before, please interrupt me, and if you don't interrupt me, I interrupt. We will have a discussion. So what is generative modeling, abstractly speaking? It is the following thing. You have a so-called latent space, which here is R to the power D, so some high-dimensional vector space. And on this vector space, you have a probability distribution from which you can sample. So you can imagine that as a unit cube in very high dimension, and you know how to randomly pick points from the unit cube. Every computer can do that, and every mobile phone can do that. So this is a random number generator. Let's not go about random and pseudo-random. So let's say we all know what that is. And generative modeling means, in one interpretation, but this is the most popular interpretation, to construct for a certain task, which I coin here by target distribution, a map G, which says the following thing, that always when I draw from my unit cube a random number, little set, which corresponds to this capital set, this random variable, and I plug this random number into my map G, then I get something which is similar to this empirical distribution. What is the empirical distribution? The empirical distribution, let's say, is the collection of all paintings in Louvre. So if all paintings in Louvre, every painting is a huge matrix which tells you which color at each point and so on, and which type of color, and all those paintings in Louvre are in this empirical distribution. They somehow tell you painting 1, painting 2, and so on, this is there. And always when I draw a random number little set from my known law and I plug it into the G, then I get something which looks like a painting from Louvre, but it's not. It's something new. It is somehow interpolated between them. This is what we call generative modeling, and the problem is, of course, I give you all the paintings of Louvre and you give me the little G. And at this point, you ask with all right, how do I do that? How do I find such a G which generates paintings from Louvre? How do I find such a map? In earlier days, one would say you need an armada of painters who are able to paint similar paintings as in Louvre, and then after a while, maybe after a week, you get then a similar painting. And then when you draw another random number, but you really need many people to do that. And nowadays we have that all in the function little g. So the question is how to construct a little g given this new empirical. And early ways how to do that, machine learning ways, were related to a structure called generative adversarial network. So this was about 10, 12 years ago. Ian Goodfellow wrote in his PhD thesis about them, and he introduced a certain technology how to train that. This was first time when you saw, maybe you remember that in the newspaper, is paintings, or not paintings, maybe just photographies of human beings which never existed, but they are somehow similar to human beings. So you could not say when you watch it, this is not a human being. It's really a good sample of a human face, even though not an existing human. But the problem with GANs was, obviously, they are difficult to train, they're difficult to construct, and there was a lot of literature how to do that. But a couple of years later, maybe now almost 10 years ago, several people had the idea to do this construction of the G in a relatively direct way. And the way is the following. I'll show the way now to you in the next slide. And this is what I mean with not so easy thing. So what they do is they say, first, I take a so-called Ornstein-Uhlenbeck process. For the non-mathematicians in the audience, just take it as a name of a stochastic process or a dynamics which is governed by a stochastic driver. And this Ornstein-Uhlenbeck process has a typical behavior. The behavior is it starts somewhere, but after a while it forgets where it starts and it moves around in a certain part of space and in a so-called stationary way. So when you observe it at one point in time and you test what is going on, and later you cannot say where you are. It's always doing the same thing. And what they did is they built such an Ornstein-Uhlenbeck process on a high-dimensional space, the space where you have all the paintings encoded, and then they let it run for a while. This Ornstein-Uhlenbeck process. What it means from the perspective of a painting is just you take a painting and you completely blur it. So this you can do as on your mobile phone. You just take a painting, let's say Mona Lisa, and you blur it such that you do not recognize Mona Lisa anymore. This is what is happening. This does not sound like generating. This rather sounds like not generating. You're just taking Mona Lisa and you blur it. At the end, you have a completely blurred picture. You take any other picture and you get the same blurred picture. So they blur the pictures, all the pictures they blur. Then, and this is now the magic, they say we learn a so-called backward process. The backward process has one thing which is not known, because everything else looks very similar. We have the alpha here, we have a Brownian motion here, we have a beta here. So it looks very similar except this middle part, and the middle part is something which has to be learned. So there is a neural network involved, and the neural network has to be determined by a learning procedure. And the magic is that they found a way how to learn this middle part. And the middle part, of course, has to be learned from the empirical distribution. So you take your empirical distribution and you learn the middle part. And then you simulate from this new equation. And you take as a starting point where you end it with the simulation before you. So you take a blurred picture and you start from this blurred picture and you run this so-called backward process. And at the end of this simulation, you obtain Mona Lisa a little bit mixed with any other picture. Why is it called backward process? Because it does essentially the following. When you have the x starting somewhere, moving stochastically into the stationary phase, so this is the x. What the y does, it starts here, it moves relatively similar, and it ends up close to here. If the stochastics is the same, but it ends in law, let's say, relative close to here. Therefore, it's called a backward process. And it is, of course, non-trivial if you have something which is forward running as a stochastic process to make the backward running thing. You have to imagine this is the de-blurring. So you get rid of the noise. This cannot be easy. Mathematically speaking, an ill-posed problem. You do something which is easy to do, destroy a picture, and then you have to build it up again. So this is what the second equation does, and therefore it is a non-trivial thing that this exists first. And I will later tell you what is the property of this backward process, and then that one can really learn the unknown bit from data. Yeah. And then, as I said, it is you take the empirical distribution, you simulate, and you get a new sampler. This is, in essence, the technology you have in DALI. This thing. It's a slightly different process, and there's a conditioning going on, conditioning on the prompt, but this is what happening there. This is different to what you have in a large language model. In a large language model, you have a somehow easier modeling setup. Here it is a priori already the modeling setup includes blurring, deblurring procedure and an object which you learn here. This is the so-called score function, the gradient of the logarithm of a certain distribution at time capital T minus little t. This is what it means that we can really learn this score function from data. This is possible. And now I can also say what Fenghui and myself are actually doing. So this technique is, of course, ad hoc. It's just written down. You write it down and you say that's it. This does this thing that I'm able, given the data and given some noise, because you plug in here a Brownian motion, and to go back, you also plug in a Brownian motion, and sometimes you even take here anyway, you plug in two Brownian motions, so you have some noise. This constitutes the set, and you have constructed via this forward-backward procedure a G. The G does the job. So this is an ad hoc way to construct it, and there is, of course, there are a lot of things to tune. You can ask, is it the only process you can take? Are there other processes you can take? You can ask, is there only one way to construct a backward process, and so on. And what Fenghui and me are going to do is we would like to understand what happens when you replace this Ornstein-Uhlenbeck process by something else. And the something else has a particular structure, namely it has a geometry coming with it. The Ornstein-Uhlenbeck process comes with the flat geometry of Euclidean space. So it somehow says every object which you are blurring here, you blur it in all space directions in the same way. And this has to do with, this is your blurring procedure. But you might say, well, in direction X, I don't need to blur so much because there, I would actually not like to change so much my picture because the X direction is something which I would rather like to keep. Or when you are maybe not talking about pictures on the wall, but maybe let's say pictures on a surface which is curved, you might want that the outcome is also something curved, and then it makes sense to associate the geometry to this process which produces something curved and only something curved. So these things have some importance, and we wanted to investigate that a little bit, but when you look such inner geometries of processes, there's a little bit of work to be done. And there's a recent work. So this is not always so completely clear how to do such things. And so there's a practical aspect, and Fenghui just showed me how it is working, this somehow state-dependent geometry carrying processes. And there's a theoretical aspect to show that you can do the same thing. And I take the remainder of the talk just to show you a little bit how this formalistically looks like to do such a proof. But before I go into that direction, I just want to take some questions.
Yeah.
If you, yes?
Like I'm wondering, like, so for diffusion models, because I'm not really familiar with that, and all the images are following one functions, diffusion models, or like different pair of images based using different parameters.
Usually you have a prompting which you have conditional diffusion models. So in that sense, you have, based on your condition, different functions.
So like each prompt has one like model or function.
Right,
oh,
right.
Yeah.
Or the network has two inputs. One is the prompt or the condition, and one is the input, the latent space, and then you sample given the condition in some part of your.
It's like for like if we want to have a really like huge like Scala, like Dalet, right?
Yeah.
We need to like train a lot of like prompt and
Yes.
image
Yeah.
pair.
Yeah. Yeah, this is how it happens. The advantage of stochastic processes is always in the fact, in contrast to PDEs or to many other objects in mathematics, it's very, very easy to sample an Ornstein-Ulm process on a 1 million dimensional space. So you have no curse of dimension when it comes to simulate. And also when you have conditional objects, this is not so complicated, but you fully rely on generalization properties of the score function, of course. This is the miracle. This is not fully understood what it works, but this is, of course, behind. But also that you're always talking about simulating of stochastic processes, which you can do in any dimension.
Maybe I just have a stupid question. So
I would be really surprised if you ask a stupid question.
this is
Let's say the first part of the statement, I think. I'm curious though.
so it's just I mean you sometimes you see the AI figures. It's for example a man with 6 fingers or something like that. So are you going to prevent something like for example in your case a Mona Lisa with 3 eyes or something like that?
No, but I would say I'm absolutely not surprised that this does not always work, because it's a very ad hoc procedure. It's a miracle that it works at all how it works. Because it is a very, very ad hoc procedure. You learn something which is obviously difficult to learn. You solve an equation backwards with this learned guide, which is not super accurate. And you do this even in a conditional way. So it's surprising that it does not give more often deviating results, in my view. But of course, it appears that it doesn't. It appears that it comes with a very high accuracy that it works very well. And this is one of the magic points of machine learning technology, that we see this phenomenon. But a priori, there's no reason to say that when you have in a, I don't know, 100,000 dimensional space where you have your images encoded, that such a type of procedure has a chance to work. So what is this generalized Langevin dynamics? I write it down in abstract terms that we have it fully at hand. So instead of talking about r to the power k, we have here a manifold, a high dimensional manifold coming together with a measure, which will be this stationary distribution which you have in the limit. And you have one generator. So this is a diffusion process, which is actually having this invariant measure as this measure as an invariant measure. So this is what we are starting at the beginning. You don't need to know about the formulas. You just should imagine you have a sort of free movement on the space, which would be in RK, let's say the Ornstein-Ulm process, and you have an invariant probability measure for this guy. This would be in the case of the Ornstein-Ulm process, some Gaussian which fits to the parameters. That's the starting point. And then you can do some constructions which all have a French name, because the French mathematicians developed that very much. And for instance, the gamma is called Carré du champ operator. You can try to pronounce it. Carré du champ operator. And you have this whole fantastic theory of stochastic analysis, which you can play here. But essentially, it is somehow so a comparable situation to R1, where I have my Ornstein-Ulm process, but just in a higher dimensional situation. And in particular, also the geometry carried by the L is one which has to do with the manifold and which can be relatively complicated. Yes?
So in French, Carré du champ means squared of the field. Why does it have the same?
It is, when you look at this operation here, L will be a second order operator, differential operator, and when you take these guys out, you just subtract the second order parts, and what you get is something like the square of the gradient of f. No, not the square, the product of the gradient of f with the gradient of g. And when you take f equal to g, then you have the square of the gradient of f, and therefore it's carré du champ. Le champ, c'est le champ de gradient. So the gradient vector field is squared. But this is, of course, in general. If you have a more complicated geometry, you have another carré du champ. And you can make a lot of gymnastics with that. But this is somehow a starting point here. Then what people usually do is an operation that they like to add a potential to this situation. So if, for instance, before we just took a Brownian motion and you take u to be the parabolic function on Rk, then you would precisely get here the Ornstein-Uhlenbeck process, and you can continue on that. So I just wanted to show you there's a well-developed generic theory how to deal with particular types of geometry and processes related to that, and you can simulate from them. And one interesting example, which we were considering in some work a couple of years ago, I think it is almost 20 years ago, and I'm really shocked about this fact. With Martin Heyer and Fabrice Boudoir, we made a little paper on as a geometry carrying object we took an nilpotent Lie group. So this is actually something which looks like Rk. And there are some standard vector fields there. They are denoted here by Vi. And you can then write a generalized version of this Ornstein-Uhlenbeck process there. And you can add a potential L there, and then you get all sorts of generalized Ornstein-Uhlenbeck processes there. So at the time, we were not interested, of course, not in reversing this diffusion. We were more interested in how quickly does that go to the stationary measure. The stationary measure is the above thing. Yes?
What is the term gradient flow? Does it associate with geodesy?
This type of stochastic process corresponds to a certain PDE. A PDE in a forward and in a backward sense. And this PDE can be understood as a gradient flow in a so-called Wasserstein space. This has a certain advantage if you consider things as a gradient flow, because if they are gradient flow, they are related to some potential, and you can then consider the PDE in a different way. This is an idea which is actually quite old and beautiful, relating Brownian motion, so heat equations and generalizations of it to certain gradient flows on Wasserstein spaces. This is what it refers to, and here this works the same way. I don't know if you Jordan Kinderlehrer Otto is one of the papers about 40 years ago where they worked it out. It's a new perspective on PDEs and a very successful perspective, but I think you can say much more about it. So ask your colleague. It does not play a role here. Here it is just we can construct an analog of such an Ornstein-Uhlenbeck process also for these general geometries. This was just a point here, and they also converge nicely to a stationary state. And now, of course, the reversion comes. How do you reverse a stochastic process? How do you do that? How is it even defined? What does it mean to reverse a stochastic process? You could just take reversing a stochastic process, start here and follow the trajectory back. This is not what is meant with the reversion of a process. What is meant with the reversion of a process is a stochastic process which is Markovian and shares the marginal distributions of the forward process. So the forward process has a certain marginal distribution, And the backward process should have the same marginal distributions, but seen from the backward direction. This is what is the reverse diffusion. It has to be a Markov process with the same marginal distributions. Now Filippo looks already because he says, okay, wait a minute, you cannot just the heat equation run backwards. You see here the equation, I wrote it for you. The derivative with respect to time of the marginal distribution is minus the generator. Minus the generator is in parabolic equations very bad. If you run a parabolic PDE in the wrong direction, you usually explode. You end up in something which is not a function anymore and so on. So it is an ill-posed question to do that. And therefore, it's not obvious that such a thing exists a priori, such a process, which is Markovian and has the same margins. Because it satisfies an equation which is a heat equation run in the wrong time direction. You remember that there was the word ill-posed. I used it already once today. Ill-posed, I said, de-blurring is ill-posed. You take a picture, you blur it, that's the easy direction. That's the heat equation forward. But to do it backward, this is not easy. How should you get that out? And the answer is you will not get it out only from the picture. You only get it out from all the marginal distributions which end at the blurred picture. Therefore, you have to ask yourself, is it possible to make out of this ill-posed equation a well-posed equation, which can only happen, Filippo will agree with it, by making the principal symbol of this parabolic PDE positive again. So how do I make something positive when it is negative? Now, I have the negative guy. I add enough positivity and I subtract it. So I don't change the equation. I add what I want to have, and I hope that I can explain the remaining part in a different way. And this is precisely what happens here. So you have the ill-posed equation from above. You add something which this, together with this, is well-posed. And this you now have to discuss harmless. You have to say this does not matter. And the question is why? Yes?
So gradient flows can be inverted in time without running into difficulties, and does this help?
If you invert the gradient flow in time, you go to.
But it's well posed for every finite time.
It is well posed, but it is bringing you precisely where you don't want to be, and quickly.
But you could say, I mean, so now the Fokker-Planck equation is well posed because it's the negative time reverse gradient flow, and all we need is now a diffusion representation.
Yes, but when you take, even if you, I mean, in finite dimensional geometry, you see it already nicely. If you take a potential which is more than stochastic, then you can invert the gradient flow, but it explodes in finite time. And take x to the power 4, and you see quickly that you run into a trouble if you run the gradient flow in the wrong direction. And in infinite dimension, this is even wider. So you quickly, with a standard initial value, you would explode into distributions. You don't have the function. But here we have a special starting point. The starting point here is a smooth object. And for those smooth objects, it works. But it has to be proved. And what has to be proved is actually that this second order term actually can be interpreted as a first order term, which is not obvious. And if you were following my little algebra, which I showed before, it is actually this little type of formula which you have here. You integrate with respect to the stationary measure. You get the L on the other side, you get the gamma, and then you have this tiny little trick that the derivative of the logarithm is the derivative of the p divided by pt, then you have the pt outside. And from this, you can conclude just by the nature of these equations that actually there is a first order operator sitting, which on the trajectory of the solution of this equation looks like the second derivative. So this is the birth of this score function. The score function is just something which comes from a derivative of the pt, and if you apply that on pt, you have a sort of second derivative, if you make a little bit of adjoint massage there. And this is then the correct score function. It does not look like a gradient, but the gamma, the Carré de Champ, as we learned before, actually has to do with a gradient. And this is then making, at least for this particular solution, this ill-posed equation well-posed. And when you then look at this equation which comes out, you get just, let me put it here. No, let me put it here. If we were going on this, or living on this group, nilpotent Lie group, you would just add to this formula here a second term, and the second term is coming from the score function. So this is a gradient of the solution of the equation. And if you are able somehow to get this guy, then you have a way how to simulate from it. So short message at the end. Even if you have a complicated geometry behind, you can practically do the same thing. You just have to replace your notion of the gradient by this Carré de Champ guy. And if you do that, sorry, I should write it back. We should replace this notion of a gradient by this guy here. And this then gives precisely the equation with respect to which you can sample backwards, and you should get the same thing. And if the geometry is chosen appropriate for your generation task, it should actually provide an additional bit of structure to your generated images. We are not there yet, but soon we will see those somehow generated pictures under geometric constraints. And well, I think I stop here and take your questions, just telling you that actually, as for generic geometries, this should work. There's very recent work of people doing similar stuff, and I don't have it here on the computer. I wanted to quote it. What are the guys? 6 guys in Stanford, or sort of Stanford, to do relatively similar stuff. Yes. Yeah. So this is somehow recent work we do. Good. I thank you, and we have time for dinner now.
Thank you very much for your last topic. So is there any questions from the audience?
Yeah, I want to ask something about the diffusion models.
Yes.
It just looks like it's a grid problem, right? And each pixel we are just like the action space. Now we see it as a reinforcement learning problem, like each pixel, how we move out the noise and turning it back into the.
There's a certain way how to see it like that, and I mean there are different ways how to get hold of the score function. And one way is a reinforcement learning way, that you say you consider your score function, which is actually not a function, but a vector field, as a control, and you try to choose a control such that you get back.
Yeah.
There are different ways how to do it. Yeah, this is one way how to do it. This is true. Yeah.
Is there any other ways like optimization? Because reinforcement learning actually it's performed quite well in like improving the denoising process.
Yes. I mean, there are different methods there, and it is, of course, the bottleneck. The bottleneck is to get a hand on this guy. This is either an optimal strategy for a reversion problem, or you learn it. I mean, there's a classical method how to learn it by integration by parts, which works very well also. There are methods when you know, like in the case of the Ornstein-Uhlenbeck process, this is a Gaussian, so you can just a kernelization technique on the. So there are different ways how to do it, but they all have their flaws. So the people still try a little bit to find out something. Schrödinger bridges is one, but there are different ways how to. Yes.
Yeah, would you please go back to page 4 on question 1 for process and type of different. Are the Brownian offices visible? This is the same. How is that the occasion for them are exactly the same, but I'll be surprised that if you.
Since it is a statement in law, it does not matter.
Okay.
But if you were really considering the question from a perspective, a pathwise perspective, you can say you have your forward Brownian motion, the backward Brownian motion. And if you insert the same Brownian trajectory, you get a path which is similar to the original path, but not the same. But at the end it is.
If it's in distribution.
It hits the starting.
The starting.
It hits the starting.
Exactly.
It hits exactly the starting point, but in the intermediate it deviates.
Okay.
So therefore, it just says that the problem of constructing the reverse Markov process, this is a non-trivial problem. It's not just going the path backwards. If it were that, it would be a little bit easier, but it is not that. This would not be Markovian.
And another question would be that is it possible, or is it efficient to apply the same techniques to, for example, time series aeration?
People try some things work, and people try to generate new returns by such a type of technique.
Okay, but then like the edge point will not be exactly the same as the starting point. It should.
But this is what we like in finance, that we are not just repeating the past. This is and here I really like to have something similar, which preserves some structures. But let's say I would not claim that such a type of technology is superior to a classical econometric technology, because there you have simpler ways to generate similar returns. So for pictures, this is more complicated. There was no classical econometric way before. For time series, there are many methods to do that well. I would say it's maybe less interesting to apply it there, but people did recently. Which, from an econometric perspective, is a very simple, not well working model. Just to say. Yes.
Of slide 11.
Slide 11.
Yeah.
Good.
You mentioned something about sleep codes and lead. I don't know.
Yes, I mentioned that with intention.
But what is the motivation of introducing lead groups? I mean, I think the photo doesn't belong to a lead group, right?
I mean, if you're a fan of Felix Klein, every interesting object in technology and science is a homogeneous space. So you have always some Lie groups hanging around. The question is, do you identify them or not? in that sense, I would say lead groups are everywhere, and in that sense, it's not so special. Why is the nilpotent lead group interesting? A nilpotent lead group is a relatively high-dimensional object. So here the K will be a large number, but I have a very small amount of Brownian motions entering here. So this is a noising, a blurring procedure which takes little noise and still puts the noise everywhere. And there you need a high level of non-commutativity, which you have in an idealized way in a nilpotent group. So you have non-commutative, 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 finish. We have reached the dimensions.
To be honest, I don't think I'm 100% sure what is it.
That's okay.
Well, I think it's like you have finite generators, but you want to generate a huge number of dimensions.
Yes.
Yes.
Yeah. I want to have many dimensions, but I don't want to interfere in all dimensions with the same noise.
It's not a question, but I would like to hear about how do you think of the flow matching models, which is a recent model replacing slowly diffusion?
Yeah, I mean, flow matching is just another way how to solve this problem.
Yeah.
So what do you do in flow matching? You replace the 2 by 1. So you only add one principal. You just make the negative principal symbol disappear. Then you have, if you can interpret the last guy as a first order operator, you have an ODE.
Yeah.
Yeah, but this is the same thing. I said there's a lot of freedom how to construct a reverse process. So I could take, instead of 2, every epsilon greater or equal than 1. 1 is flow matching, 2 is reverse Markov process, 10 is an extreme reverse Markov process. So there's freedom here. You don't even need to take the same L. You can take a different L. It just has to dominate the other negative symbol. Yeah.
Professor, like actually doing experiments on training different like differential models, we are considering about like adding some constraints and anchors at the very first beginning. That means for your Gaussian distribution at like 0, t equals to 0, like how can we better add these kind of anchors or priors, etc., to the entire distribution?
I mean, if you have a Gaussian distribution, it's a little bit hard to constrain it to stay somewhere, at least precisely. You can say it rarely goes in some space directions, but if you want to do it precisely, you will not be able.
Yeah, but like, is there any kind of like solution way or like ways?
You have to reduce this geometry into the generator, and then you get the different invariant measure. Yeah. The constraints have to be in the object on which you run. Where are you doing that? Where are you doing these experiments? So
because like currently I'm like working on different meta projects, so like we are running parallel training these models on the student clusters. And the reason we are trying to like figure that out, because in the real life, for example, when you design some auto-driving policies, you try to add some like human-like driving ways. Because like currently end-to-end auto-driving policy design, they are like using different kind of neural network training. However, they can only output 1 or 2 certain outcome. But like in the real life, human will have like different scenarios. For example, when raining, when have like sunny weather, when have dog across the street, etc. So like people are using diffusion models to try to train these kind of neural networks. So yeah, we are trying to improve that.
Okay. Maybe you write me an email. I would be interested.
Yeah, that makes sense.
Yeah, please.
Yes. So when people are training the diffusion models, usually they do not directly learn the gradient of the entire distribution or the density function. They instead learn the noise. They have the neural network input with the noise picture, and they learn the noise.
And probably this is why we don't need the neural network to respect the geometry of the data too much, because it was parameterized to learn the noise, but not the gradient of the density. I mean, the gradient would be difficult to learn from empirical distribution. So what you usually do, or one method, what you do is you make an integration by parts and you get the training problem involving a first derivative of the network on the noise which you generate. This is what is one of the methods how to do it. For the network, it does not matter so much what it respects or not. The question is, do you want that your reconstructed picture satisfies some constraints? So for instance, imagine that you are in R3 and you have pictures which are on the sphere, but you do not take spherical coordinates, you give them as R3 things and something. So you would like that the reconstruction really stays there. And there you have to include a certain geometry in the blurring process, because you're never blurring in this direction, you're only blurring here. And by the gradient which I introduce here, this all respects the geometry and does the good thing. So the neural network carries no geometric information. It's only the blurring and de-blurring process which carries geometric. And this technique, what you say that you can just learn on the noise which you generate, this you have the same. And this is a very simple integration by parts again. This here and then. As a follow-up, maybe I'm not sure that if you generate a stochastic process, then you try to use your method to enforce that let's say distribution you get at the end is still marginal or something. No, once the Nürnberg process is never a lot. So I mean, if your samples is a process. Let's say the distribution you are starting with is a stochastic process. Yes. So you get a lot of samples from a martingale, and so you have two time dimensions. First is the time of the stochastic process, and another continuous time is the time reverse of the quantum process. Yes. And by enforcing some kind of the structure or your this remains all the same. There's no so a martingale, as you know, does not mean, and also here you have a certain drift which is always there, but it does not mean that it goes everywhere in space. I mean, the one-dimensional Brownian motion in dimension 2 is also the martingale, even though you never see the second dimension. So this does not interfere.
Other than this OW process in the zoo or tree of other process, which other alternative you think is also doable, like the next paradigm for generative AI or etc.
I mean, this is just a trial, what we do now. So this is still in the paradigm forward, backward. Generalized OU just means that you have an invariant measure, and otherwise the process is completely general. So in that sense, you cannot generalize that. That's it. It's the most generous thing you can take. It was just a question whether it works with this technology, whether it can work. But we will see.
Okay, I think sorry we have again time limit, so let's thank the two speakers again. Of course, the lecturers, if you have more questions. So let's.
I have to leave now. Thank you so much for the.
We prepared some gifts.
Thank you so much.
Very
good.
Also, thank you. We have prepared the gift the host. And thank you all for coming.
Thanks a lot.
Is it possible to take a picture?
Thank you all for coming.
Yeah.
Okay. Amazing, crazy.
Yeah.
We have to find people look. Even like that so many of you will come. Okay. And then